I built a solar power system for winter field day, but I almost forgot this step. For winter field day, we decided to add the additional challenge of running solar power for all of our radio gear. This is great practice for a grid down emergency. I want to show you the system I built and walk you through the components and why I chose them. You may ask, why didn't you just buy an EcoFlow? Well, there's two reasons for that. The first reason is the cost. The EcoFlows could cost over $1,000, to where I was able to build this entire system for under $500. The second reason is by having individual components, it's easy to troubleshoot and replace those components if there's a problem. We'll start with the input. On the input side where the solar power is coming in, I decided to put a 50 amp circuit breaker. This serves two purposes. It gives me some protection in case of a short, and also allows me to easily disconnect the power in case I need to do any maintenance to the system. From there, the power goes into a Renogy Wanderer solar charge controller. This is a PMW solar charge controller that's capable of 30 amps, which will easily handle 300 watts of solar input. I also opted for the optional Bluetooth module, which allows me to monitor the performance of the solar panels. From there, I go to a terminal on the circuit breaker that connects directly to the battery. This is a 200 amp circuit breaker that gives me protection to the inverter and allows me to shut off power as well. So from the battery, it goes to the circuit breaker, out of the circuit breaker into the inverter. The inverter is a pure sine wave inverter, giving me clean power to the radios. It provides 1,000 watts of continuous power, but can handle a surge of 2,000 watts. You may ask, if the radios could run on DC power, why would I use an inverter? The simple answer is, we want to maximize the power coming out of the radios, and we want to be able to run anything additional that we may need. So let me explain. The radios we're using require 13.8 volts for maximum power output. The batteries are only providing 12.8 volts. By the time you run from this board 50 foot on 8 gauge wire to where the radios may be placed, you're going to have a voltage drop across that line of about 1.4 volt, giving us 11.4 volts to the radios. So they're not operating at their maximum. As well as, I don't really want this equipment right next to the radios because it could cause noise. That's the reason I went with the inverter. We could run 120 volts directly to the radios at any distance we need, not have the noise, and be able to run it through a power supply then, given the radios 13.8 volts, so we get maximum output. I had a Grenoble 100 amp hour battery on hand, and I decided to go ahead and add a second one. This is the step I almost forgot. I'll be connecting these two batteries in parallel. Now, you don't want to just go ahead and hook them up together, because if the voltages are off, that could cause some issues. You could cause one battery not to charge properly, which could lower your power capacity. It could also permanently damage the battery to where it never charges fully again. The other issue is the inrush of current could cause one of the batteries to explode. That's something I definitely don't want to do. So to remedy this, first you want to charge both batteries to their full capacity. Then take you a voltmeter and test the batteries for voltage. We'll do that now. So on my first battery, I have 13.24 volts. On the second battery, I have 13.42. That's not too bad. I wouldn't worry about that. But if it was off any more than that, what you would want to do then is connect the batteries using a 2 ohm 10 watt resistor. This will help balance the power between the two before you connect them permanently. So that's the solar system I'm using. What's your plans for winter field day? Let me know in the comments below.